started with a project that we have been working on, and the project is called QUBIP. QUBIP stands for Quantum-Oriented Update to Browsers and Infrastructure for Post-Quantum Transition. So basically, QUBIP was designed to contribute to European PQC transition and streamlining the process for creating a replicable transition model. So all over the Europe, QUBIP has 11 partners, including us from Finland, which is Tampere University. And at Tampere University, we are responsible for integrating state-of-the-art PQC implementation in OpenSSL and NSS through shallow loadable modules. So what are shallow loadable modules? We will get to it in a minute in our next slides, and we will have a look on a brief look on how do we integrate the post-quantum cryptography in the OpenSSL and NSS on the client side. So if you are, as I said, we have 11 partners, so every partner is working on a different building block, and we have a series of blog posts at qubip.eu/blog posts where you can read what we do in our projects and how we are contributing in different using different building blocks in the PQC transition. This is the geographical representation of our partners. As you can see, most of our partners are from Italy, Spain, in Czech Republic, Red Hat, and that's us from Finland. So QUBIP started back in September 2023, and it's going to end in next summer. And it's a 3-year project, and we will be the goal of this project is one is the transition to PQC, and from our end at Tampere University, we are trying to make OpenSSL and Firefox more crypto agile. So moving next, we will now be presenting the pilot system overview of the project. In this pilot system overview, as you can see, we have the structural diagram of our PQ-enabled server on the left side, maybe the right side of yours, and the other side is the PQ-enabled client. So I will start with the server side, and then I will let my colleague Francesco to explain the client side. And on the server side, we have Fedora 42-based host, and on top of it, we have our server instance with Nginx, which is powered by unmodified version of OpenSSL 3.2, and the main component in the server side is the Aurora. So what is Aurora? As we know that the OpenSSL allows us to play with the OpenSSL provider property, so we at Tampere University developed our own provider, which is Rust-based, and it's called Aurora. So what Aurora does, it's a shallow provider. As I said, what does shallow means? So this provider does not contain any PQC implementation at all. So it allows external PQC implementation to willingly engage and disengage with the OpenSSL and work. The idea behind this was, let's say today we have the PQC algorithms now, and with the time period of, let's say, 5 years, 10 years, we have more matured PQC algorithms. So what we will do, anyone who is using our version of OpenSSL provider, they can simply disengage the previous implementation and seamlessly integrate the new implementation in the OpenSSL and use it. In here, I also want to mention one thing, that to make this possible for Aurora to become a shallow provider with the methodology, what we did, we actually crave out the interaction of the user application with the libcrypto of OpenSSL, and we introduced our own layer that allows the integration of external implementation. We call this layer as adapters. So for now, whatever implementation we support at the moment in our server side, it has a corresponding adapter in the code base and for the corresponding PQC implementation. So let's say if we are supporting MLCAM, so it will have its own implementation, will have MLCAM supported adapter, which will interact with the OpenSSL. And On top of it, I also want to mention one more thing, that we have an upstream Rust-based crate, which actually allows any one of you to create an OpenSSL provider based in Rust. So if you are looking to work in future for creating an OpenSSL provider from scratch in Rust, you can refer to our crates, which is upstream. And this crate actually is not the expertise or the, we don't have the time to talk on it, but tomorrow, one of our colleague or our supervisor will be presenting a talk on OpenSSL, this Rust crate, and we call it OpenSSL Provider Forge. So if you're interested, please do attend that talk as well. Now I will like my colleague to take the floor and explain on the client side and explain how do we use our version of server, QUBIP server, and QUBIP client to actually establish a PQ-enabled TLS 1.3 connection in practice.
OK, so for the client side, we run our own version of Mozilla Firefox that from now on I will call the QUBIP Firefox. And it's essentially a fork of the upstream Firefox that has been powered with post-quantum cryptographic support. So most of our changes regard NSS, which, as you may know, is the cryptographic library that is being used by Firefox. And in order to enable full integration, we had also to refactor those components that live within the Nico subsystem that depend or interact with NSS. So to enable support for post-quantum algorithms, we leverage the design model of NSS. So NSS has been developed with the PQC TLS standard in mind. So we are not actually entirely replacing the already built-in soft token in NSS that is being used in Firefox, but we are loading our module. So our module, as you see here, is called Crypto Token, and it's a shallow PQC TLS software token that acts as an intermediate layer between any external post-quantum cryptographic library and any application that is built on top of NSS, so in this case, Firefox. So it's worth mentioning that our crypto token is actually a fork of the upstream Cryoptic. Maybe some of you attended yesterday Jakob Ellen talk on Cryoptic, but we actually diverge a lot from Cryoptic in the sense that we removed any OpenSSL dependency, and we actually provided a layer, an abstract layer that allows the user to load external post-quantum libraries. As you can see from the picture on the top left, we have a verifiable credential wallet. So it's there because it has been implemented as a Firefox extension, but is not something that we will see today. But it's there because it's part of another work done by another one of our partners, which is the Links Foundation. Back to Keith.
Yes. Thank you, Francesco, for explaining this. While Francesco prepares for the live demo, I would like to explain the 3 use cases that we covered in our QUBIP project, but for sure we will be covering today in the demonstration only the first one, which is the TLS level server authentication. So we have the QUBIP Firefox build, and we will establish a PQ secure TLS 1.3 connection with QUBIP server instances, which are currently based in either Finland or Italy, using our crypto token, which is our QUBIP soft token. And let's see. And the last 2 of them is the app-level user authentication via plain text and the authentication via PQ anonymous credential, which is the verifiable credential wallet. And this is actually at this time out of the scope of this demonstration. So let's see. Let's go with Francesco. All back to you, Francesco.
OK, so for the demo, I have prepared a clean Fedora 42 virtual machine where I have already installed our QUBIP Firefox, and I've already prepared and initialized our crypto token. But if you are interested in reproducing the exact step that I'm going to show you next, and you want to install our QUBIP Flatpak Firefox version, or you want even to play with it, so you want to build from source either Firefox or crypto token, you can find all the detailed instructions at github.com/qubip/cryptotoken. So let's jump into our QUBIP Firefox. So as you can see, our QUBIP Firefox is based on the dev edition 141.0 So the first thing I will see is we'll go to the Italian QUBIP web server landing page. So the connection to this website is still exchanged with hybrid post-quantum algorithm. So we are still using the already built-in X2519 MLChem768, but the signature scheme that is being exchanged is still a traditional one. And also the certificate chain that comes with the server still contains traditional digital signatures. So if we go to use case 1, we try to negotiate post-quantum, in this case MLDSA65 signature scheme. And as you can see, we get an error. So what is happening here is that our Firefox is able to recognize the actual algorithms being exchanged, but there is no module, so there is no token in the slot list available for those algorithms. So there is no PQC11 mechanism able to handle that. So to solve this, we go to settings, and here, if we go in the security devices, we can load our token. So I will just give it here a name, and I will load our shared object file because our crypto token is dynamically loaded inside Firefox. So now I will log in. For the sake of the demo, I just use 1234 as password, but also use stronger passwords. So now if I refresh the page, as you can see, the error disappears, but a new warning appears. So essentially what Firefox is telling us that there is no certificate issuer known, so we are not able to build a certification path up to a trust CA. So we can solve that by going back and downloading our TLS CA certificate. So once it's downloaded, we can go back to settings and view certificates above. In the authorities tab, we can import that trust CA in our trust store. So we want to trust this CA to identify websites. So if we go back to use case 1, as you can see, we successfully connected using MLDSA65, X2519, MLChem768. So, and also if we look at the certificate chain coming with the server certificate, you can see that the end entity certificate has been signed with the MLDSA65 signature algorithm. So we also want to show to you that if we inspect the page and we go to the network tab, we reload it, and then we get the response and go in the security tab. I can grab this. OK, so we are using, as a signature scheme, correctly, MLDSA65. And as a key exchange group, we are using the X2519 MLChem768. So there is an ongoing development for testing other algorithms, so post-quantum signature algorithms. And if we go to the finish landing page, if we go to use case 1, of course, we get, again, this warning because we need to import other root CA. But what we want to show you here is that we are actually using SLHDSA for signing our intermediate TLS certificate and the composite MLDSA65 T219 to sign our end entity certificate. Of course, we are not using SLHDSA in the handshake because it's not feasible. But I want to show you the moment in which you look at the certificate chain. So if I add our root CA, and I trust this again, it's not this one, sorry. OK, so if I go to use case 1, so we successfully connected because we are still using the same signature scheme in the handshake. But if I look at the whole certificate chain, as you can see, we get the entity certificate that is signed with MLDSA65 T219, and the intermediate certificate has been signed with SLHDSA shake 256 small. And the same also for the root CA, but of course this is a self-signed certificate. OK, so what we have showed you so far is an integration testing with our server, but we want to show you that we are also interoperable. So for doing that, we can go to Open Quantum Safe interoperability test server. So here we can find other servers that try to negotiate other post-quantum algorithms. So if we go, for example, to MLDSA again, well, we support all of the parameter sets, so we could go also with MLDSA 44, 65, or 87. But also here, of course, we get the same warning, but for simplicity, and also we don't have time, we just skip this because we don't have any trust CA in our trust store. And as you can see, also, we successfully connected. So last but not least, we can try also the Cloudflare research test page. So as you can see here, it tells us that we are post-quantum secure with the X259 MLChem 768. But right now, this page does, like this server doesn't try to negotiate any post-quantum signature scheme. But why we are showing you this? Because well, from the moment in which we load our token, so as I said before, like Firefox already has the support for this hybrid key exchange. But in the moment in which we load our token, we can handle the post-quantum part of the key exchange with our token. As you can see here, it works, and we are post-quantum secure. So that's it for the demo. So conclusions. We have seen Aurora and OpenSSL provider Forge for our OpenSSL post-quantum cryptographic provider, and Crypto token for the Firefox NSS compatible PQC 11 token. Here we have some direct links to our blog post, which track the progress and give also more technical details on what we have done so far, and so future work. So we want to match the new NSS. So what I didn't say before is that some of our patches already landed on NSS 3.116. So there is ongoing effort to upstream the support for MLDSA. But as I said before, our QUBIP Firefox is a fork of Mozilla Firefox. And Mozilla Firefox NSS is in turn downstream to the main NSS. So we are also downstream to the Mozilla Firefox NSS. So once there is a new refresh inside Firefox, we will, of course, rebase and match the new NSS and maybe drop our changes. So then we also want to demonstrate mutual TLS. So we want also to demonstrate client authentication with post-quantum algorithms. And then, of course, we want to rebase on the latest cryptic because we actually forked more than 1.5 years ago, so there are a lot of changes. For the Aurora, instead, we want to showcase adapters using dynamic linking. And of course, we want to also for Crypto token provide a little bit of cleanup and maximize code reuse before they release. Thank you.
Yes, this concludes our demo. And me and Francesco are happy to take questions from you guys if you have any.
Do I correctly understand that SLH-DSA is related recently completion from your side, right?
Yes.
OK, great. And one more technical question. You mentioned that your fork of Cryptic gets rid of OpenSSL implementation. What do you mean? If I remember correctly, the original Cryptic just borrows OpenSSL sources and wraps it with the providers. Am I wrong?
Yes, but like we just turn off that, and we are, for the moment, only statically loading external libraries. Like for our MLDSA, for example, we are using libcrux. And the idea is that we want to give the user the ability to actually load new different algorithms as the different libraries that implements cryptographic algorithms as the landscape evolves. So that's the main point.
OK, thank you.
Thank you.